to each other. Okay, let's go to our class. So we have the exam on Thursday during the class time. With the caveat, if you signed up with the center, the disability center, you got a letter which also forwarded to me and haven't contacted you, please send me an email right away. I already talked to some, and please come to the office hour after the class. The exam again will be during the time of the class, 8:10 to 9:25. So I tune the problems accordingly so they can be finished during this time. For this, I need you to have paper ready and pencil ready. When the exam will be becoming accessible, like the homework as an assignment through Canvas. So you have to have access to Canvas, at least to download it once or to print it. You do not have to print it. What I'm interested in is your answers on paper. And then at the end, we will have 5 minutes more and 10 minutes more. And you will scan your answers and upload in the answers exactly like you did for the homework. So we are in principle practiced in this part. Questions up to this point?
Yeah, will there be anything like a cheat sheet or anything like that that we need to bring?
So I have uploaded already a formula sheet that you definitely have at your disposal, and you may want to print it. In addition to that, you have one more page, front and back, where you can write all those formulas you think will be relevant.
Okay, thank you.
Yeah, and this can include anything you see relevant. I recommend not to put pre-calculated problems there. This will not help you. Yeah, so in addition to the formula sheet, one more sheet, both sides, where you can write the formulas you felt necessary to do the exam too. And what I need you to do is, when you upload them, you have to clearly mark which problem you address on the page. Even better if you number your pages before you scan them. I usually put a number per side, and I would like you to do that too. So in case in your nervosity something gets messed around or so, we can sort it easily out. If there are no further questions, the material is clear. I said all, including 3.3, the discussion of potentials as we discussed up to the last lecture. And you may have also realized from the problems, this is actually the problem number 5, which would you give an indication up to what point I covered the Griffiths material. If there are no questions at this point, let's just step through the test exam, which I planned for today. So again, you do not need the clickers today. And the exam will be constructed exactly this way. Are you able to see it? If not, you also should have it in front of you through the homework, or maybe you downloaded it.
We can see it.
Okay.
Dr. Spanier,
Yes.
are you going to be recording this class?
Yes. From now on. When I, yeah. Okay.
Thanks.
Okay. And I'm going through the answers of these questions. So the exam will be constructed exactly like this. There will be first 5 questions, you may say, similar to the clicker questions. So in preparation, also revisit the clicker questions, which were more to the concepts rather than doing explicit calculations. What I'm trying to do is I actually try to switch the camera around. And so I will stop sharing so that the whiteboard becomes, oops, should pop up. It should show as the prominent. Let me see what happens here. Can you see the whiteboard as a full projection on your screen?
Yes.
Okay. Because somehow okay, good. Okay, so the very first question asks, if the total charge enclosed inside the Gaussian surface is 0, then the electric field E, in this case, I indicate a vector by printing it bold, everywhere on the Gaussian surface must be 0. True or false? If you answer, you have to give a reasoning.
I said false.
You said false because some reason?
Because you could have like a hollow spherical shell, and if you took a Gaussian surface inside that spherical shell, the electric field would be 0.
Yeah, but then you say it's 0. If you say false, you need to convince me why it should be non-zero. Or did I misunderstand?
Because you can have a perpendicular electric field to the surface of the Gaussian, right? And it's still 0. So it can be a non-zero constant, but still the surface integral can be 0. So it's false, right?
Yeah, but if you have a non-zero field perpendicular, it is still non-zero.
The surface is the surface.
At the moment you can draw a field line.
Couldn't an exterior charge contribute on the surface while still providing 0 flux from within?
I do not say it has to be a conductor. But what about this example we had? If I put a dipole in there, the enclosed charge is 0, obviously plus and minus is 0. But when we drew out, or if you think about the field lines now, if you draw them out, they're more complicated, and in particular, they're non-zero everywhere. Of course, enclosed as enclosed charge, or the enclosed over epsilon 0, if you would apply Gauss's law, which we also discussed is not appropriate really anymore because we are breaking the spherical symmetry here. It will not help us. So you could just say, starting with a dipole already, this is not true anymore. Yeah. So the moment you can give one example, in this case, we discussed a dipole. You have answered, or you have given a reasoning. Okay, number 2, A spherical region, radius r, centered at the origin, has electric field E of r equals 0 throughout. The voltage V from r must also vanish throughout that region. True or false?
False, because it could be a constant, right?
Correct. Huh? If, I don't know, you would reason, in principle, you can just write this as writing down the definition. How do you get actually from the field? And if you then plug it in, you would write 0 plus a constant. No? If you integrate along r. And that's the integration constant. So I try to keep them to really, you can make the answer to the point, relative short. The indication that you can do so should be that there's not much space. But since you have your own paper, of course, you could continue. Warning, do not spend too much time on this. But you get this 1 point in this case for having the right intuition, say false. But I need to see the reasoning to give you the full points. So for the third one, the spherical region, radius r, centered on the origin, has voltage VR equals 0 throughout. The electric field E from r must also vanish throughout that region. True or false?
True, by the same reasoning, v equals negative integral E dot dl.
Okay. I would start what the quantity is. It's fine, yes, but we're asking what the electric field must vanish. So E is given as minus the gradient of E, and then that's minus the gradient of 0, and that's 0. No? But yeah, this would be the more direct way to say it. No? I want to know something about E given V, and so this is how I make the connection. In the previous question, it was the other way around. Then number 4. The charge density is given as xy as function of x, y, and z, and is given as c del x del z minus 2. How does it actually look? What does this represent actually? This is just a more complicated way to say, to describe what? Any idea?
If it was like a full 3-dimensional Dirac delta, it would be a block sphere, right? In 3 dimensions. Or maybe not a block sphere, but it would be a sphere of unit 1. If it was just the normal delta cubed, right? But
this
instead,
yeah.
we have x at 0 and z at 2, and then a line along all of y.
Okay. Here's 2. Here's 0, 0, 0. So x is 0. Yeah. Just pulled into this point. In z, we are pulled in this point. And as you said, along y, it is still free to go, no?
Yeah.
So it will be something like that, a line. And then C is what? Or what is this to begin with? This is our line charge density, no? Because now it only depends on one coordinate. And so now I ask, what's the unit of C? Now we could do it step by step.
Coulomb meters?
Sorry?
Coulomb meters?
Yeah. No?
I got a little misrepresented in my case. When I did the homework, I looked at rho and I assumed it was 3 dimensions, and I put coulombs per meter, like, or per unit volume. I didn't think about the fact that it was a line charge. Is that going to be like super bad on my grading?
Yeah, that's kind of missing the point.
Yeah. Okay.
Because we used this, or I demonstrated it to you, right? This is exactly the trick, to stay very generic in, for example, calculating the charge or whatever, calculating the or the potential rho over r, etc., etc. No, where we then integrate over the volume to add up the charges first, and we can use the general form, the three-dimensional form. If you look at Griffiths, he writes, okay, if you're three-dimensional, you use rho. If you're two-dimensional, you use sigma. If you're one-dimensional, it's lambda. So you have to be very careful how you write your dq when you integrate. In principle, you don't have to be if you're consistent and you write all your distributions first in such a way. And to argue, you could first write the unit on the left side, which has of course to match the unit on the right side. This is Coulomb per cubic meter. But then you also would have to tell me what's the unit of the delta function. We discussed this. It's kind of, it appears, it has to deal with the unit of the differential here. No. So each one of them is a 1 over meter. So I get 1 over meter square out of this. So I'm left with 1 over meter. So this all adds up nicely. But good, you got it now. So and then number 5, derive the differential form of Gauss's law starting from the integral form. Now this is really just reviewing how it's done. Gauss's law. The surface integral of the electric field is equal to the integral of the divergence over the volume that's enclosed by the surface. And how do we turn this into, we also know, sorry, this is the enclosed charge over epsilon 0. And this is, of course, we just had it, no, this is 1 over epsilon 0, and now integrate the charge density distribution. And so here it is kind of ready. The thing is we're integrating over the same volume here. Expression 1 on this side, expression 2 on this side. So we can pull it out. Oops. And that would be the differential form. You should write the same. Yeah. So this is really nothing new at all. Questions up to this point? Okay, then problem number 2. Yeah, any question?
Yeah, I have a quick question. I'm sorry, I'm just confused on how to draw 1.4. Do we have 2 lines or 1 line then?
How to draw? This is a line which follows the y-axis at z equal 2 and x equal 0.
Okay, great. Thank you.
Okay, now a fixed spherical shell with inner radius A, outer radius B carries charge density, and then there's a charge density given as k over r square, and it only carries it in the region between A and B. I didn't provide a drawing. I highly recommend whatever the problem is, draw it first out. It helps to organize and understand. So A and B are the two radii given here. And actually, let me stop sharing again so the whiteboard becomes dominant projection here. So you better draw it first out. And it's about this region where the rho is actually given. This is where the charge sits. And rho is given as k over r square, or the radial direction of r. And it asks you to calculate the electric field in the three regions. And it would be really good to just state the strategy after you sketch the outline. How do you calculate the electric field? What approach would you take? What did you take?
Yeah.
Yeah. Practically what we just discussed in 1.5. No, you use Gauss's law. You can take your Gaussian surface and then enlarge it. It leads immediately to a trivial answer in the region where you stay below A. Is the radius, namely. So it's good to write it out, let's say. So E dA is Q enclosed over epsilon 0. Let's not bother ourselves with the divergence. And this, of course, we get again by doing the integration. So the last, if you were able to answer 1.5, then easily, then you know what to do here. So what is the answer for r smaller a?
0.
Right. So the enclosed charge is 0, no? Just looking at the drawing, no? And hence here. It is also nice if you would just indicate your final answer, because it may happen you step around. I recommend to be very systematic and sequentially develop your answer. Don't get too nervous or train yourself, or you have by doing the homework, I hope. But definitely indicate the final answer here. And then A smaller r smaller b. Now we are in this region where we place the charge density. So in this case, it is more involved. This is the one where we actually have to calculate, no, the enclosed charge. You may also just write Q enclosed. Rho d tau, copy this from up there. But now we have to write down what we mean by the integration. This is in R, no, from A to some R. This is only R dependent, so I can write this right away here. It's good to indicate this R here is the integration R. So then it becomes K R prime square. And then the integration is R square prime, no, the R prime. So this R square in principle belongs here, but I wanted to indicate I'm doing the R integration here. No? The full volume element is R square dr, the cosine theta d phi, and accordingly now we have to do the cosine 1 or sine theta d theta. And then d phi from 0 to 2 pi d phi. Since there's no dependence, this gives us a 4 pi. The r square cancels here, so the integral itself is actually relatively easy because it's just r, no? So we get 4 pi k, and then epsilon 0, not to forget. And then r prime here from a to r, so it's r minus a. That's the enclosed charge. And now we said this has to be equal, again, to the integral over the surface here. Is spherically symmetric. I can pull E in front of the integral, but then it just becomes E times 4 pi r square. Oh. And now I just solve this for E, and I make sure I carry around also the direction of E, which is along R. So solving this becomes K over epsilon 0. K you may plug in. So I always run around this K here. This is of course 1 over 4 pi epsilon 0. We have agreed on this, so you may not have to spell it out, but maybe to be complete, I'll write it out. But I keep it as K of epsilon 0, r minus a divided by r square, and then r. And that's the box. And then the last region, let me see if I fit this here, r crater B. Do I have to actually step through the full calculation again? What changes? You could write this.
Instead of r minus a, you get b minus a.
Because?
All of the charges contained between a and b, so your integration unit or your integration boundaries would be from a to b.
Correct. No, that's the change. Now I do have an upper limit here at b. And so indeed, here I would have b minus a. I solve it accordingly. And so in principle, I'm already done. It's also k over epsilon 0, no? And then b minus a over r square. And of course, still r. Any of such time savers, if you tell me after integration, AB dr prime. Yeah. The reason to give you a certain time is, of course, not to demonstrate all the steps in all detail. If you see this, like we just did, then write this down and give the answer. Okay, and finally it asks you to sketch this. Now this means to draw. Let's see. It would be nice to open a new page for this, or at least put it on the back as I did. If I put it here, can we still see it? Here you draw E, magnitude. This is R, the two important radii are A and B. Now in this case, you can simplify. If you draw E divided by, and then we just divide out this constant, because then it's really just an R, A, and B dependent expression. So I divide out K over epsilon 0. Then I know also that, okay, that's the trivial part. It's 0 here. At B, it reaches a value, and we know actually the value. And you just plug it in. And this is B minus A over B square. This would be to really have the complete discussion of this plot. And this we reach here. Outside, it's just 1 over R square. No, I may not really get the curve completely right. You may just indicate what you mean here. So this is proportion 1 over R square. And the middle part is a bit more complicated. So you may try to break this maybe down in 2 more points to understand actually how it actually evolves. So R minus A over R square. No, this is it's tricky because this is a 1 over R minus A over R square. So on a calculator with a little table, maybe you break it down in 2 more points so you see, in fact, how it moves, but it moves something like that. And that's the answer. You could write here proportional to R minus A over R square. What I did not, so questions up to this point, sorry. Yeah. You don't have to be precise, just give an idea. But it would be nice for complete documentation to, for example, mark the maximum here. What I did not ask is the potential. Let me not do this right away, but we can come back because instead of the field, actually not instead of the field, because in this case, the easy route would be to first go through the calculation of the field and then use the relationship between field and potential to get the potential. As you remember, the potential is given as minus EDL, but we will need a reference. Would give it to you the natural choice in spherical symmetric problems with a limited charge distribution is to put the reference point at infinity. No? So V from infinity is 0. And this means we have to integrate from the outside in to some inner R, say. But due to the fact that we run through different zones here, we will have to break this down and accordingly plug in the electric field that applies in a given zone before we reach all the way inside. And to give the potential in any of this zone, you would start carefully outside in. So you go from here. The first one is from infinity all the way to B. And from B, if you want to know through here, then it continues to A. And then you go inside with R. As I said, I keep this if you have still time to also remind you of how to do this. Any questions on this? Then I take this. I forgot to mention, I posted the solutions of homework 1 to 3 next to the homeworks. You probably have seen it already when you open Canvas, which I recommended to do regularly. But if not, please have a look there. And I will add after class my notes here on what we discuss right now. So problem number 3, a positive point charge plus Q. Actually, let me just share. See, I asked you to sketch it. And of course, you could have guessed. The two zones you have probably got just by looking at the problem. Inside, you know, is 0, so this one is fine. Outside, we know it should look like a point charge because it's 1 over r square, because now we have all the charge enclosed. It's spherical symmetric. We go away, we expect it to be 1 over r square. This you get right. So right there, you have it. So the tricky part is really just the in-between part. Think about it like this. So don't give up. If the calculation ends up in a mess, you still can continue and answer the other questions, possibly. So a positive point charge is fixed distance a in front of a conducting grounded plane. Another Q2 is placed on the z-axis at distance 2a. What is the charge Q2 that one needs at the 2a position so that the positive charge A does not move when let go? Now this implies we need to turn this into a static problem. The forces have to add up to 0 in this point. Okay. Here we go. Again, we better draw this first. Everything happens along one dimension x. Somewhere there is a conducting plane. And we know where this is leading up to. This is an image charge problem now. So I put at A this charge Q, and at 2A I put Q2. So this is positive. This we don't know what it is. Our plane here, just to indicate, it runs perpendicular to the x-axis. Here's the mirror charge. And minus A here. I found minus Q. This is the first image. And over here, I find minus Q2 if I get this plus. And to generalize this, ultimately what we want is Q2 is some alpha Q expressed in units of Q. So I know I need, do you guess which sign alpha has?
Negative?
Yeah. But you don't necessarily have to put it here right away. You could. But it just flips around one more sign in the problem right there. So the net force on this charge has to be 0. And then it's good to write down what we mean by force. We mean K, Q, some other prime, the second Q, depends now when we step through here, by the R square. And in this case, long R, and R in this case is whatever distance along the x-axis between these charges. But we expect this to be, or z-axis. I wrote x here, I'm sorry, in the problem it says explicitly z. This is, of course, not a problem if you mix c and x, so as long as you stay consistent here. And so, in these problems where several charges are involved, it's good to start labeling them. 1, 2, say 3, and 4. Then we have 3 force contributions, no? We have 1, 2. We have 1, 3. And we have 1, 4. I could have been more explicit here by making an index here. that will be even more detailed in explaining what's going on. So now I have to really just write down the terms. And I have to be very careful about directions and charge signs. So the first one between 1 and 2 is proportional QQ2. The distance between the two of them, that's A, so it becomes an A square down here. And I have to not forget my factor K. I could also write just K comes later, because it's of course on any of these terms, but this would be the full expression. We are missing, of course, the direction, which is critical. So this goes in positive Z direction. This is the first one. F13, K, this is minus Q square over, they are separated by 2A, so it becomes 4A square. And now the direction in this case, minus Z. Yeah, that's critical. And then 1,4, accordingly, K, Q minus Q2, so it gets minus QQ2. The distance is 1, 2, 3A, which makes it 9A square. And the direction, minus Z. Is of course the total force given now as the sum of the three contributions here. Fj in this case now, because they're all with respect to the same Qi. I was 1. I equal 1 in this case. I'm becoming more and more specific as I go along. And now that's just mass, no? Now I plug in. I do not forget that I still have no real idea about the Q2, so I plug in this. So if you do this, I pull out the Q here over A square, and then it reads as Q2 plus Q square, and then plus Q2 over 9. And now I plug in for Q, the alpha. This has to be 0.
Dr. Spanier, shouldn't your middle term be divided by 4?
Yes. What happened? Oh, thank you. So this would be what I would call a nervous transfer error. And it's, of course, a different story to do this on the whiteboard. Talk and write. So please focus. But if it happens, it seems obvious, no? What happened? So this will not give you the real boomer in your points. Because now, of course, I would make a follow-up mistake. What I did, I looked at my paper instead of thinking.
What's the second Q squared? Shouldn't it be not squared because you already took 1 Q out?
Yeah.
Okay, thanks.
I did something you are not going to do. I just looked at my paper and just copied instead of thinking and just making the actual transfer. That's not a good idea. Don't transfer things from one paper on the other. That would be my advice, because that's where things happen. No? If you copy and then I continue from here. Try to avoid this.
That's what partial credit's for.
That's partial credit, yeah. Like I said, it will not cost you the points here. But also to avoid this, just by experience, the moment you start looking and you say, okay, now I copy, copying always has a much higher risk that something like this happens. But if you continue and you multiply this out, because we require it to be 0, we don't care about this anymore. No, we can take now 1 more Q out, because Q2 is expressed in terms of Q. So I'm only concerned with the alpha, so I get something like 1 alpha plus 1 over 4 plus 1 over 9 alpha here. That's 0. And now I can solve this for alpha. And you find this is minus 9 over 40. Make a nice box around it. So the negative sign, indeed, somebody mentioned it already. We don't have to. It should come out naturally. And it's a bit of an odd ratio, of course. But that's okay.
So in practice, we can have fractional charge.
It is given in some charge, which is of course macroscopic, say microcoulomb. This is not an elementary charge which you have to split. Huh? So wow. So this could be 1 microcoulomb. I don't know, we want to discuss this now, but if you take the charge, now I place this as individual charges. The number of charges I would have to place, is the 1 microcoulomb divided by 1.6 times 10 to the minus 19 coulomb, which is the charge of the electrons. That's an enormous number. It will be very easy to get the 9 over 40s of this. Make sense?
Yeah, I just automatically assumed it was a unit charge of some sort, so I didn't.
No, we are not there. Yeah, we're putting charges on spheres. On a balloon, you rub it on your hair, and this is not a problem. This is slightly modified because in this case it actually just says, and now I need to carefully flip here, that we place explicitly minus q the same charge here now. And we are asked for the electrostatic energy in this setup. The electrostatic potential energy. Again, it's good to write, after drawing, to write the expression we want to use to calculate this. Develop it, so everything becomes the next natural step. And some of you may fail or do a stupid thing like I just did, but then it's clear you're on the right way. And the expression in this case over the combinatorics here, I write this as index I, charge I, compared to J. I is smaller. J. So it's placing or moving the charge I into the potential of charge Q. The potential is given as Qj over the distance between them. All right, J, and then I multiply this by charge Qi. K, our proportionality constant, or 1 over 4 pi epsilon 0. Is this complete or not? Am I missing something? I'm missing the factor 1/2 here. Because we are talking about mirror charges or image charges, and the field or the energy in the field is only on this side. This one is shielded by the conductor plane here. Yeah, so do not forget in this case the factor 1/2. If you forget it, it's a follow-up mistake, but this is a more serious mistake because you forgot that you have to take care of only half, or that you are calculating it on one side here. This comes for free. The placement of these charges comes for free. The moment you put this there, this is there. And in the conductor we will have no problem to move them around. So again, I labeled them 1, 2, 3, 4. That's important because now we have to really sum these combinations. 6 combinations, no? 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and then 3, 4. So we have 6 unique pairs, and I recommend to do this very systematically, to write them out. 1, 4, and then 2, 3, 2, 4, and then 3, 4, and them up later. So here, just for bookkeeping, the first one, that's minus q squared over a, no? And then accordingly, 1, 3, this is minus q squared. And in this case, it's 2a. And then the third one is a positive 1 over 3a, q squared over 3a, and so on. I think it's clear. So if I sum them up now, here I actually calculate the energy as the sum of the individual terms. And that's q squared over a, which I can, of course, pull out everywhere. So I'm left with, this actually comes about between 3, 4, 2, no? It's the same. So this is twice, so minus 2, then minus 1/2, plus 2/3, and minus 1 over 4. So some terms appear twice. This is just an offset here, no? This and this is the same. And so if you do this times k, in this case not to forget, and of course the factor 1/2. Then you get something, and I wrote this down in fraction 1/2. You can do this if you don't want to use your calculator right away. I did it like this. And if you solve this, then it becomes minus 25 over 24, and then kq squared over a, which is about minus q squared over ak. What does it tell us? What does the negative sign tell us? Let me ask you, comment on your result. What does it mean for this problem? What does it represent?
This is the amount of work it took for us to move the charges into the spot?
Yes, and that means negative sign indicates. What does a negative sign indicate on a work? Negative work. What does it mean? You released the energy. Well, no. As a potential energy, negative sign also means you end up in a state that's energetically preferred compared to having them away from the state. So it works in favor of you to create this configuration. Later on, what it will indicate to you is it's a bound state. Now in this case, we fix them at places and not naturally stay there. We only know it's negative. We could try to find the minimum in the setup. Which way would they stay, if there is one? In this case, you would call it a bound state. I don't ask you to go that far, but you can tell me that negative sign indicates that this is a preferred configuration, or the energy is set free. You remember this from your previous class. Negative energy means, oh, negative work, what negative work means. Questions? I think this was all on 3, yeah. Question?
Yeah, why were you able to consider all 6 configurations for energy, but not all 6 configurations for force?
Now, this is the way we defined the energy, is of successively placing charges and getting to this configuration by adding up individual contributions to the setup, and we ended up with this expression. By force, to get to the energy, we still would have to do the integration of the force to replicate this. But the force is always between 2 charges, and I add them up by a superposition.
Okay, so I have a second question as well. You also said in this problem that we removed the conducting plane. So if we removed the conducting plane and treated them as such, as they were all independent charges.
That's right.
That wording to me says that we don't, I mean, why would we use the 1/2 formula and not?
In this case, you wouldn't. I'm sorry, but I did actually have the old version of this question in front of me. You're absolutely right. You're absolutely right. So if we remove, that's the difference. If we remove this, if I take this away and I just place the charges as indicated, in this case, the whole result will be a factor of T2 larger, no? So times 2. And if you made the same mistake I did right now, that's an easy fix. You just write in the end times 2, because in this case I removed the plane.
I guess I'm still kind of having trouble because I'm kind of kicking myself in the face now, because I actually worked this problem and have it work just like this, except I questioned myself and said, well, if all of our forces are going to act on one object, then all of our energies need to come from the configuration based on one object. So I don't understand the difference between why we only chose one set of configurations for force as opposed to 3 types of configurations totaling up to 6.
Because in the first part I say we place this charge to A and the others are there. So what's the force on this particular charge? Everything else is fixed there. It's a given. We don't care. So we want to only know what happens to this one here.
Okay.
One charge. Everything with respect to this one charge. The second question says, okay, removing the plane, if you leave it there, it's exactly what I discussed. If you remove it, same thing, no? What is necessary to place them one by one by one by one? So the very first one, that comes for free, but the moment you take the second one, now you put the second one in the third of the first one, but the third one will have to be placed in the field of the first 2 ones, in the potential of the first 2 ones.
So because you focused on just one charge, which was why you could just do one family of, okay, so that makes a lot more sense. If I were to build them all and not have the conducting plane there, then my force would have to include all 6 configurations.
That's right, but good, I made this mistake, or I have the old version. In both cases, the calculation is the same, and the only difference, if I construct it this way, is this factor 1/2 here, no?
Gotcha. Now I understand. I thank you.
Right. Okay. Yeah. So read very, very carefully. Yeah. The first one, indeed, only this one charge. Everything else is there, and now where is it pulled? The second one is building this whole thing, with or without conducting plane. Without conducting plane, it's even more straightforward to explain it. No, it's placing one by 1 by 1, always in the field of the previous one. Yeah, so don't panic. Like I hopefully didn't panic using this old version, explaining it to you. You can always explain it later. Oh, no, and times 2 because there is no plane. But you need to recognize this, what it means. Is there a factor of 1/2 or not? Okay, and then problem number 4. Actually, let me quickly check. Oh, you have it in front of you. Yeah. Do I need to project it? Let me read it out. So there's this, in this case, I provided a drawing along X. There is a line charge. It's limited between 0 and L. Uniform. And in this case, we want to calculate it over here. I called it already x0. This would be the x, and actually the x prime. Yeah. The x prime, the location where the charge sits, this would run here between 0 and L. But it's good one way or the other to distinguish the indices. So the question in this case is, calculate the electric potential along the x-axis. So Vx0, 0, 0, if I write it as a 3D problem. From x0, and how is it given? What relationship would we use in this case?
If you're asking for the formula, it would be k times the integral of lambda over r, the absolute value of r.
Yes. Or if we break it down one step before, we of course need to integrate up the charge, the dq here, over r. So what is dq? I give you this table to carefully break this down into steps. In this case, the dq is exactly what you said. No, this is lambda dx prime. And the r here, this is our old r twiddle actually, no? The relative distance between where we place the charge and where we measure at x0. This in this case is of course just x0 minus x prime. So it would be nice to break it down and state the ingredients. And here we want to specify that x0 is greater x prime. So now, yeah, now it's plugging in. It's perfectly fine if you right away plug it in. If you have the time, if you think you have the time, it's better to again first write down the strategy or the setup. Because again, if something happens, whatever it is, up to this point, we knew you are on the right track. So now I'm just plugging this successively in, no? x0 minus x prime. And instead of looking it up, no, it looks really nice. And it makes it nice if you do the substitution here. And du is minus dx prime. And then the limit x prime goes from 0 to L. We should probably do this here. And accordingly, this runs from x0 to x0 minus L. No? And then it becomes just a du over u with a minus sign. And of course, you know, that's a logarithm. So if I write the answer here, this is k lambda. Lambda uniform goes in front. Ln And then it's the ln of u from x0 to x0 minus L. So then it becomes x0 minus L over x0. Or if I take the negative sign in, I can flip the ratio around. But that's good enough at this point. You got this? Just to indicate, I could have taken this away and then make this minus L here. Then it reads nicer without the negative sign. But both are, of course, the same.
But wouldn't that be detrimental to the next part?
Yeah, you have to be careful. Not detrimental. It shouldn't change anything, right? I can take the negative sign anytime back out. Yeah, so the next part is how does it actually behave? Yeah. So what you want is, of course, x0 much larger than L. And like you just said, now you want to break this out. But you have to be careful, of course, because we're in a logarithm. So you can do this by going back, no? Like you just said, so it becomes and this goes to 1 if I let this go to infinity, and therefore it's 0. That's what you meant, I guess. Right? But you could also try to find the Taylor series for logarithm. And so I give you a hint. For example, if you write ln 1 plus epsilon, in this case, it would be minus epsilon. So you flip the sign, but to get to epsilon, you have to flip the sign here too. So if you do this, if you develop this, you find this L over x0. And that means if you actually had fully analytically written it out in approximation, this becomes k lambda. And then you get this L over x0. But this is good enough. If you arrive here, that's even better. Okay. Do we still have time? We should, because it was meant to be solved within class time. Question? So the final one, that's indeed a potential problem. And in this case, the potential is given. Remember, the other version of the problem is to give actually the charge density on the surface of a sphere, sigma from theta. In this case, it's given as sine squared theta half here. Case sine squared theta half. We have to be careful with the case now, of course. This is not the 1 over 4 pi epsilon 0. This is a constant. And it asks for inside, for r, smaller r. And that means we have an ansatz for the Laplace equation. So first of all, this is what we want to solve. So it's good to write this down. And solution ansatz, that would be the part that gives us the behavior inside. Oh. If you want to be completely detailed, you write, of course, first a boundary condition. There are two of them. One was v from r to 0 finite. And number two was the V from r theta, once you reach the surface with r, has to be V0 from theta. So that outlines the full strategy, what you're going to do here. And then the solution answers here, that's the AL, and then RL, and then PL, the Legendre polynomials. PL, oops, Legendre polynomial. If you have put this together, the rest is really executing the thing. So this is the result of boundary condition 1. And number 2 written out means V capital R theta has to be is AAL capital RL PL, and this has to be our K sine square theta half. What's the next step?
You want to find the coefficients, A, Isabel?
Yes. And how do I do this?
You would want to multiply, you'd want to integrate and multiply by another orthogonal Legendre polynomial.
Mm-hmm.
And the orthogonality property would give you the ability to use K sine squared theta over 2 to find A's.
Mm-hmm. So you can indicate, multiply by PL prime, and integrate out the cosine theta, and then use orthogonality / completeness of the Legendre polynomials. And it is helpful to get a DLL prime on both sides. This is an angular function. This is a function of theta. So the question is, can we describe sine squared theta half in a way as a sum of Legendre polynomials by itself, so that we get only specific terms here. In this case, it's a bit of a gymnastics. You may develop this by yourself. So cosine theta is cosine theta half plus theta half. Now you use that this is cosine squared theta half minus sine squared theta half. Or you have a couple of these relationships on your cheat sheet. How can I re-express cosine in terms of sine, so sine square? Or you develop it. I mean, this is straightforward. I did it here on the sheet to develop this. What you find is that sine squared theta half indeed can be given as 1/2, 1 minus cosine theta. And this tells you how to break this down. No, this is also then 1/2 P0. P0 was just the 1, and then minus P1. So indeed, we only have the 0 term and the 1 term. If we go back here now, plug this in, K 1/2 P0. This will project out P0 and P1. So we can write, from this we find on the left side A0, R to the power of 0, P0 plus A1 R to the power of 1. P1 has to equal this term here now. K half P0 minus P1. And now I can solve this. This means A0 is K over 2. And A1, that's just minus K over 2R. Indeed, the boundary conditions led to a complete solution. I mean, allowed me to find all the coefficients. And so I can finally write the final result. I write it here. I'll probably write this now below. The final result. And it would be important to write it down, really, because we want the expression for the potential is 1 minus R over R cosine theta. And again, make a nice box around it. And that's it. And we should still have a couple of minutes over. Let's see. No, we are just in time. So I will likely reduce the effort or the total number of things I ask in terms of effort somewhat reduced to fit into the time. So by now the time is over, and by chance we finished all. Any questions? Do you feel up to it?
I mean, I'd have done pretty decent if this was the exam.
Okay.
I would have probably put my head through the desk, though, on problem 3.
Again, if you write carefully down what you're doing, and it's clear where it went astray. So go through the clicker questions one more time. This will answer the first part, conceptual questions. Revisit the problems you calculated. It's not at the level of the homework or at the level where you have encountered the calculation already. And I just ask you to repeat it. Maybe it will not be involved and may ask you more to understand the strategy, or like in case of the wire we calculated, in principle you have encountered it before. If there are no more questions, I also still have the office hour right after this. I asked two people to definitely come to the office hour. Send me an email so I don't miss you if you want to still talk in the office hour. Good luck. Bring pencil, bring paper.